So reminders and announcements to get started. Um, there should be a homework 3 that's available soon on Canvas. This is going to be entirely on Canvas, and it will not really involve any programming. And this homework will cover everything that we've covered in the semester so far. Think of it as an excuse for preparing for the midterm. It's not like the homework is going to look like the midterm, but to answer the homework questions, you'll have to revisit all the stuff we've seen so far. And the midterms, of course, is on March 6th. And it will include material that we have done in class till this Thursday, till 27th. The exam is going to be self-contained. It's completely closed book notes. You don't need your laptop. You will not need a calculator and so on. I'll try to post some sort of a study guide type thing on Canvas. I think a couple of you asked on Piazza about this. So you'll see something on Canvas by the end of this week. Are there any questions about this? It'll just, so the question on Zoom is, will there be a practice exam or just a study guide? It'll just be a study guide. I have been told, and people who, my TA who took my class last semester can tell me that my midterm tends to be rather hard. I didn't feel that when I made it, but apparently I'm not the target audience. Just letting you know. Any questions? If there aren't any, there's another announcement. This is about the project milestone that's due today. This is rather simple, and many of you have already done it, so thank you for that. All you have to do is join the project on Kaggle and download the dummy submission that we've already given you, and upload it back to Kaggle, note down the performance metric that Kaggle tells you, and report on Canvas what your Kaggle username is and whatever the dummy submission returned to you. This is just like a sanity check to make sure that you have the workflow set up. Of course, the real work starts only after, where you'll be doing actual submissions on Kaggle, but this is to get the workflow going. This should be rather simple, right? I mean, those of you who did this didn't hopefully take too long. It's just creating an account on Kaggle if you've not got it. And I think there was some clarification on how to find the performance metric on Kaggle, on Piazza. So I hope this is not occupying too much of your time. It's due today, and it's worth a small number of points so that you actually do it. So please get it done. Any questions about the project? About this milestone or anything in general about the project? There aren't any. There's another couple of fun announcements. These are things that you've seen already. A second request to participate in this online survey from Professor Samir Patil and Annabelle Warner, who's a student. It involves how trying to understand how you may use AI. If you do use AI, or if you feel like you have something to say about that, that QR code will take you to the right place, or maybe that URL here to tell you more. I don't have anything more to say about this than what you can read here. So, help your fellow student do their research. The other thing is a distinguished lecture/discussion. Don Norman is a giant in the field of usability design, and he has in some sense defined the field, and he's visiting us this week, and he'll be giving he's going to be answering questions on Thursday at 5:30. If you do not know who Don Norman is, you can look up his Wikipedia page or his innumerable lectures that are on YouTube and his discussions. He talks about some rather fun stuff, and he seems like an interesting person to meet. It's not often that interesting people show up at one's doorstep. So if you can attend it, I understand that the timing is not great. It's at 5:30 p.m. on a Thursday. But if you can attend it, it promises to be interesting. Again, don't ask me questions. This is something that you can find information about on, I think if you go to the CS department website, you'll probably find information about this. Have people heard of Don Norman before? A small number. It's he's had an outsized influence on how we interact with technology, in terms of making things usable. If not for people like him, we would all still be writing messages inside terminals and using Emacs, which some of us still do, but apparently there are other ways of doing things. Okay. Any other housekeeping stuff to get out of the way before we dive back into computational learning theory? You all are awfully quiet today. Okay, so I can see that you're all eager to go back to computational learning theory, so let's do that. We're talking about computational learning theory. We are in the middle of a series of 4 lectures on the topic. The beginning, we first talked about this idea of the theory of generalization, and we looked at probably approximately correct learning. And we also saw this one theorem called the Occam's razor for consistent learners, which we then applied to get some learnability results. Some types of concept classes are learnable according to sample complexity, and some of them are not learnable. The standard counterexample for something that's not learnable according to sample complexity is the set of all possible Boolean functions. Today, we are going to look at something called agnostic learning. The important point that we've seen is in the context of the one Occam's razor theorem that we saw was we were able to examine the question of how good a classifier that's consistent on a training set will be on future examples. So you have a classifier that's perfectly that assigns the correct label for every example on the training set, and you have m examples. How well will this classifier generalize? What will its error? What's the probability that its error will be less than epsilon? And that was essentially what we looked at. And we developed a bound that's something like if you have more than 1 over epsilon times log size of h plus log 1 over delta, if the number of examples you have is more than that, and you have a classifier that's perfectly consistent with all of them, then with high probability, with probability more than 1 minus delta, your classifier will have error less than epsilon. So let's think about all the assumptions that went into place in order to derive that expression. We assumed at the beginning that the test and the test examples and the train examples come from the same distribution. We don't know what the distribution is, but we assume that it's fixed. So examples are sampled from a natural process that does not change. Then we assume that the hypothesis space is finite because we talk about this quantity here. How can you measure the size of a set if it's not finite? Then finally, we assume that for any concept that that nature might choose, there is some function inside our set that is consistent with it. So for any concept, we will be able to find a consistent hypothesis, right? So we made these 3 assumptions. So today, we're going to look at that last assumption. Can someone convince me why that last assumption is not reasonable? Yes.
Less on that it's particularly reasonable and more just it seems like it's a very strong assumption that this is going to hold for all concepts that we could come across.
Why? I'll give you an example to make your life easier. Imagine that the concept we are trying to learn is whether a certain image contains the picture of a cat or not. Or it could be cat or pick anything you want. How could you possibly hope to know what the concept class is to begin with? First of all, what is the set of functions from which nature creates a cat image? If you knew that, haven't you already solved most of the problem? The other way to think about it is, in real life, we never know what the target concept is, but we don't even know what set of functions nature uses to pick its target concept. When I introduced the notion of a concept class, I said, imagine that there's a set of functions from which nature chooses the true function. It's easy to imagine it, but we never know what it is. So if we do not know what the true set of functions is, how could we possibly hope that no matter what concept from that set nature chooses, there's a function in your set that you have picked that's consistent with it? Does that make sense? You cannot possibly know what, you cannot possibly guarantee consistency with an unknown set of functions. So if you want to put it, let's look at it slightly differently. So far, we always assumed that the learning algorithm could find the true concept if one existed. So the picture might look something like this. If the inner circle C is the concept class, and the dot represents the function that nature chooses, your learning algorithm is exploring a set that contains the dot. Which means no matter where the dot lies inside that circle, the set of functions your learning algorithm explores contains that dot. So your learning algorithm has a hope for finding something that's consistent. But maybe we do not know what that set C is. And so we're trying to learn a concept using a hypothesis class that may not contain the true function. We're not saying it does not contain, it may not contain the true function. This setting is called agnostic learning. It's agnostic to the choice of the concept. It's agnostic to whether the true concept is in the hypothesis class or not. And the question that we are interested in is, if we cannot make any assumptions about whether the true concept lies inside the hypothesis class or not, can we say something about, is learning possible? Can we say something about sample complexity? Can we have a bound of some sort that says, if you have these many examples, then you'll be at least this good. Your classifier that you learn will at least be this good. And I would argue this is a more realistic setting than before, because we make no assumptions about whether the true function sits inside your hypothesis class or not. In fact, even this picture here is a slightly optimistic thing. It could be something like this, where we have a set of functions that nature chooses, and we have no idea where that set is. We have a set of functions your learner explores, and we are hoping that there are some guarantees about the function that your learner finds. Now, this is a more realistic setting. Like, for instance, imagine that you're learning a decision tree of depth 3. I keep picking 3 because I don't know why. 3 trees is a very hard thing to say. So let's say we are picking a decision tree of depth 5. So depth 5 trees are a set of trees. And you're using that to on a data set that you don't get to control. And maybe that data set has been labeled according to some phenomenon in nature. Let's call it the true concept. You have no idea what the true concept is, which means you have no hope that there's a depth 5 tree that contains the true concept. And the question is, in that setting, can we say something about the quality of the tree that's learned? Does the setting make sense? At the end of today's lecture, I hope to convince you that we may be able to say something, even though we don't make that assumption, which is kind of strange, right? I have no guarantee that the true function lies inside the set that we are looking at, and yet we hope to be able to say something about the quality of the function that's learned. Questions? Or let me ask you a question, or let me make you think about a question. In the agnostic learning setting, first of all, we are no longer guaranteed that there's the training error is 0. Because it's possible that there is no function in your hypothesis class that can match all the examples in the training data, which means you can get some non-zero training error. Right? So now the question is, what can you do? What's the best you can hope for? Yeah, you seem to have an answer. So you can hope for low training error. And then what? What about the future?
You have enough examples, then hopefully the error stays small.
Okay, I'll repeat that in case it didn't get on Zoom. You want to minimize the training error, and hopefully that error stays small in the future. Did you have something?
Yeah, it generalizes better on the future one.
You can't expect it to generalize better, but you are hoping that it does not generalize much worse, which is a somewhat pessimistic but maybe more reasonable thing to expect. You can't expect it to do better than the training data, in general. But that's roughly the intuition. You can't hope for it to do perfectly on future examples. That was a hope that we never had to begin with. But here, the only thing that we are hoping for is it does not do too much worse in the future than it did during training. So let's now revisit the notion of errors again. We've seen this before, so I want to just reintroduce this idea. We can find a classifier that has low training error. And just as a reminder, the training error, if you have a set of examples S, your training error is the number of you iterate over all the examples, you ask how many of them your true function f and your hypothesis disagree, you count how many such examples exist, basically the number of instances where the number of training examples where your classifier that you're learning disagrees with the true label, and you divide by the number of training examples. So that's the fraction of examples where your classifier makes a mistake. That's your training error. You can try to find a classifier that has low training error. But this is, of course, not what we want. What we want is to find a classifier that has low generalization error. The generalization error is simply the probability of making a mistake where h of x and f of x are different on an example that's randomly sampled from this unknown distribution that also generated the training data. So what we want is a guarantee that a classifier that has low training error will also have low generalization error. If we can somehow guarantee that, then maybe life is good. So that's what we're going to try to build up to. Before we do that, any questions about the plan? We're going to build a guarantee that says, if your classifier has low training error and you have a large number of examples, then it might also have low generalization error. Effectively, we are asking, can the empirical error on the training set somehow give us some information about error on future examples, on examples that we have not yet seen? Have people seen something like this before? We will be building on tools that you may have seen to answer this question. Kind of a neat exercise in a neat sort of a probability puzzle turns out. And we'll be looking at the proof today. The technical tools we'll be using are called tail bounds. Have people seen tail bounds before? You must have seen tail bounds, I don't know, 5th grade or something, where you're first introduced to Markov inequalities and such things. You're laughing, no? Okay, 6th grade. Basically, we are asking how far a random variable can get from its mean. So these things are called the tails of these distributions. I mean, this is just a cartoon example that I pulled out of Wikipedia. Don't read too much into this picture. But let's kind of build it up one step at a time. You may be familiar with, of course, the law of large numbers. If you collect more samples, the empirical average becomes closer and closer to the actual expectation. So if you have a coin with an unknown probability of producing heads, and you want to discover that probability, you can toss the coin many, many times, and you can count the number of heads divided by the number of tosses. And as the number of tosses increases, this ratio of number of heads divided by m becomes closer and closer to the probability of heads. This is by the weak law of large numbers. There's nothing, this should not be a shock, right? Hopefully not. But the thing that we don't know here is how fast do these two terms converge. This expression says as m tends to infinity, we get closer and closer to the true probability. But it does not say how quickly the gap converges. Or it does not actually say anything about the gap. It just says these two things get closer. But you may have encountered other theorems that actually talk about these kinds of gaps. You know, Markov inequality. Have people seen Markov inequality before? 1 thumbs up and 2 head nods. So that must be 100%. So it's basically saying what's the probability that a certain non-negative random variable exceeds the mean. And it says it's not too large. It's less than the expectation divided by, it doesn't have to be the mean. It could exceed some value, A. It's the expectation divided by A. And using the Markov inequality, you can also prove something called the Chebyshev inequality, which is what's the probability that a random variable differs from its expected value by some fixed multiple of its standard deviation. So random variable, mean, fixed multiple of its standard deviation. And Chebyshev's inequality says it's 1 over k square. It's less than 1 over k square. You may have encountered these before and in some probability class, and you may have solved some homework questions around this. And if you have some vague recollection of this, but can't really put your finger on where to use it, the good news is we won't be using them. This is just to kind of put you in that frame of mind of what kinds of tools are we looking at. What we want is actually it turns out, we want to be able to bound the sums of random variables, and we'll see why in a bit. Well, we'll see why right now. Turns out that the training error is really is proportional to the number of mistakes that your classifier makes. And the mistake your classifier makes can be seen as a random variable. And so adding up all those mistakes divided by the number of examples is your training error. We want to be able to bound this. We want to be able to bound the training error, and neither of these things really work out for us. What we want is a new inequality. We have Markov and we have Chebyshev. We have a new class of inequalities called Heffding's inequalities. Have you seen Heffding's? I think doesn't the data science, the foundations of data science talk about Heffding? Maybe it does, yes. Heffding's inequality talks about, it assigns an upper bound on how a sum of a set of random variables changes from its expected value and how fast. So let me give you an example. Suppose you perform an experiment m times and compute the mean. Basically, you toss a coin m times and you calculate the fraction of times you see heads. You can ask, what is the probability that the true mean is more than epsilon away from the empirical mean. You can ask, what's the probability that the value that you calculated is, in some sense, is underestimating or overestimating? I always get the inequality wrong here. Basically, you want to ask what's the probability that the true mean is more than epsilon away from this p hat, which is the expected, the empirical mean that you've computed. And what Heffding's inequality says is, if you perform this experiment m number of times and you care about a very tight bound epsilon, then this quantity is less than e power minus 2m epsilon square. Now, don't ask me how to prove it. If you want, I can point you to ways to prove it. Just take it as a theorem for now, because we're going to build on top of this. So what this means, so let's think about this. P here is the true mean. So for a coin toss, it's the probability of seeing heads. It's the thing that you want to estimate. P hat is an empirical mean that's computed by tossing the coin m times. And what this expression says is, this is asking the probability that the true mean will be more than epsilon away from the empirical mean that's been computed over m times. Heffding's inequality says that probability is going to be less than this quantity here. Now, let's look at the quantity on the right, this thing here. It's e power some expression. Importantly, there's a minus m. E power minus m means as m increases, this exponentially drops. As the number of trials increases, the difference between p and p bar is going to get very, very small very quickly. The second thing is, it says, if you want your epsilon to be small, you have to pay a bigger price, because epsilon square shows up there. So if you want the gap to be really, really tight, then you need a very big m for this to for those two things to. Epsilon is a number between 0 and 1, right? If you want epsilon to be really, really small, epsilon square gets even smaller. So m has to be really large to counterbalance that, so that this e power thing becomes small. So basically, if you care about a tight bound, then you need to have a very large number of samples. Now, you could have said that even without this theorem, right? If you want your, let's go back to the law of large numbers. If you want your empirical probability of heads to be very, very close to the actual true probability of heads, toss the coin many, many times. This is asking, how quickly does that convergence happen? Any questions about this? Yes.
How is epsilon determined?
Epsilon is not determined. This is almost like a, it's a statement that says, if you have a certain epsilon and you want to know what's the probability that this probability is more than epsilon away from p bar, then it's bounded on top by that expression. That's it. Epsilon is not determined. Epsilon is a parameter that for different epsilons you get different bounds. If you demand a very, very tight bound, in other words, your epsilon is really tiny, then your m has to be very large. That's it. Other questions? Yes. Oh, that's related to the proof. That's related to the proof, but it's very convenient for us because that it talks about exponentially fast convergence, and it is for now, take it as a given. Yes.
In the case we have infinite number of samples.
Yes.
That is m is infinity. So the right side would become less than equal to 0.
Yes, which means it's equal to 0. Which means the probability that I think there must be a greater than equal to there. Yeah. Good point. Yes. And this is one side of, yeah, that's a good technical observation. I believe this should be greater than equal to. This is one side of the Heffding's bound. There's also another sign where you have a less than. Basically, what ends up happening is if you have an infinite number of things, it's sandwiched on both sides by it should be greater than equal to p plus p bar plus epsilon. It should be less than equal to p bar plus epsilon. It gets sandwiched and becomes equal to p bar for any epsilon. Okay, so what does this have to do with agnostic learning? So I set up a certain question. The question that I asked was, I have a classifier that I need to train, and I have no idea whether the concept class sits inside the hypothesis class, and I need to derive sample complexity. I asked the question and then went into this detour about Heffding's inequality. It turns out Heffding's inequality provides us the technical tool that we need to answer that question. So suppose we have a classifier H, and we want to measure its generalization error, error sub D. Error D of H is nothing but the probability that f of x is not equal to h of x. It's a probability, right? But I could treat that probability as a random variable. I could treat that error as a random variable, just like in the previous example, I could treat the probability of getting the true bias of the coin, the probability of heads from the coin, as a random variable. So I'm going to ask, what's the probability that this this generalization error is not too far off from an empirical error that's computed on the training set? The empirical error on the training set is error S. It's simply the fraction of the training examples that have been misclassified. So I have this random variable, error D, and I have error S, which I can compute using an experiment. Instead of tossing a coin, I'm going to every training example and asking, is this incorrect or correct? Is H incorrect or correct? So the random variable is H is incorrect. What am I writing for? This is my event. H is incorrect, and I can ask what's the probability that H is incorrect, and that's exactly the same as error D. And I can now, you see the analogy to the coins. Coins giving heads is like H being incorrect. The coin producing a tail is like H being correct. My training set consists of m examples, and for every single example, I can ask, is H incorrect? In the coin, I have m tosses of the coin. For every single toss, I can ask, is the toss producing heads? I can ask the coin, what is the fraction of times the coin produced heads? I can ask the training set, what's the fraction of training examples where H is incorrect? So now I can apply Heffding's inequality. What's the probability that the true error is more than epsilon away from the empirical error? So I can apply Heffding's inequality, and let's do that. So the probability that the true error is more than epsilon away from the empirical error is bounded just from Heffding's by Heffding. It's bounded on top by e power minus 2m epsilon square. Before I move on, any questions about how I got here or why I got here? Importantly, is the analogy to the coin tosses. Does it make sense? Does it not make sense? One of those things you need to nod your head, right? Yes.
Just to clarify, so we're setting an upper bound probability of our training error being epsilon away from our true generalization error.
I would put it the other way, the generalization error being epsilon away from the training error. Yeah. Yes. Why do you ask that though?
Just to make sure my understanding is correct.
Okay. The intuition for that is, if you have a training set and your classifier gets a low training error, and you can ask what's the probability that your generalization error is also going to be low. It's not going to be too much more, how much more? Epsilon than the training error. So there's a question on Zoom, why do we care about this probability? And that's the answer. We care about this expression here because we can measure the training error, and let's say that the learning algorithm that we have is a very, very stupid learning algorithm that just enumerates every possible hypothesis and finds the one that has the lowest training error. And let's say that low training error is something small. Now we can ask, what's the probability that the generalization error of that particular classifier is not too large? It's not too much more than whatever training error that classifier found. And Hefting tells us that that's less than e power minus 2m epsilon square. We're not done with this though, because we are going to now we're going to take this and massage it a bit more to actually come up with a sample complexity bound. Does that answer your question on Zoom? So what we have here is the probability that any hypothesis, by the way, this is not necessarily true for the best hypothesis, the one that has the lowest training error. This is true for every hypothesis H. The probability that a single hypothesis has a training error that's more than epsilon away from the true error is bounded by e power minus 2m by 2m epsilon square. The learning algorithm, hopefully, if it's doing anything reasonable, looks for the best one in the entire set of the hypothesis space that we have. So we're going to play a game that we played before. Exactly the same thing that we saw for the previous setting. The expression above is true for any hypothesis, and the learning algorithm finds one of them. So notice that this expression here, the error D is greater than error S plus epsilon, is actually a statement of a bad event. If error D is greater than the training error plus epsilon, that means that there was a classifier H that has low training error, but the generalization error is actually bad. The generalization error is more than epsilon than the training error. So we are going to call that a bad classifier. A bad classifier that somehow managed to get fooled by the training data into having a training error of only error S, but its generalization error is actually more than epsilon, more than that. Epsilon is some sort of a threshold that we care about. So this is a bad situation. We do not want our learning algorithm to be fooled by such a classifier. So this is a bad situation that we hopefully we can ask, what does it take for this bad situation not to happen? Yes.
So are you basically saying if a hypothesis, if the training error, being some epsilon distance greater than the true error, if it's greater than that E part, then that's a bad hypothesis?
Yeah, so let's put some numbers into this, okay? So let's say the training error is 0.1. On 10% of the training data, your classifier has made a mistake. And let's say your epsilon is 0.1. That means this is asking what's the probability that your generalization error is more than 0.2. And maybe I don't like that. I want my generalization error to be less than that. I want my generalization error to be as close to 0.1 as possible. This is a bad situation where the generalization error is more than some threshold away from the training error, which means the training data is no longer representative. The training data fooled your learner into thinking that this is a good classifier by giving it only an error of 0.1, when in fact, your generalization error is actually more than 0.2, which you don't like. Does that help the actual numbers?
I guess I'm just wondering what happens if that probability is greater than this lower bound term? What does that?
This expression here,
Yeah, what if that expression is greater than e to?
it's not. It's not. By Heffding's theorem, it's provably less than e power minus 2m epsilon square.
So there's no case where it will be greater?
No. Take that as a theorem. That's a statement of fact. Or take that as an axiom, if you will.
Alright.
So this is a bad situation. The probability that, or the event that your generalization error is much, much worse than your training error is a situation that you do not want. By much, much worse, I mean more than epsilon away. And we would like to somehow try to make that an improbable event. But even before that, this is for just one of the hypotheses, little h. Your hypothesis space has a whole set of them. And you don't know which of them your training algorithm is going to pick. Maybe your learning algorithm is not particularly a good one. Maybe your learning algorithm just randomly picks one of them. Right? You don't know what it's going to do. So let's be extremely pessimistic about your learning algorithm. We could ask, what's the probability that there is some hypothesis in your hypothesis space that has a training error that is whose generalization error, is more than epsilon away from the training error. The probability that even one such hypothesis exists. Maybe, see, think about it this way. Let's say your hypothesis space has 100 functions, and 99 of them have this property that its training error is lower its generalization error is within epsilon of the training error. And one of them is bad. One of them has the property that the generalization error is much, much worse. And maybe your learning algorithm is lousy and it picks that one thing. You don't want that situation to happen. So it's a very pessimistic situation. We could ask, what's the probability that there is some hypothesis in your hypothesis space such that it can get fooled by the training set? And the union bound simply says that quantity is less than the size of h times e power minus 2m epsilon square. We've seen the union bound before. Does this seem familiar? Yes, one person has seen it. Where have you seen it? Sorry? Oh, you've seen it. Well, you saw it in graduate algorithms, but you've also seen it when we proved Occam's razor. The union bound is simply saying that if you have probability of A or B is less than probability of A plus probability of B. Probability of A or B or C is less than probability of A plus probability of B plus probability of C. And there's always a less than equal to here. Probability of one of a set of events happening is less than the sum of the individual probabilities. Instead of a sum of individual probabilities, I'm just multiplying by size of h because all of them have the same right-hand side. So and there are the size of capital H such things that you're adding. If you've not seen, if I guarantee you've seen the union bound before. You've seen it before, maybe you've not seen it with this name, but you've seen it before. I want you to revisit this and think about this. For now, just take it as a given. Because I want to kind of build on top of this. I want to keep moving on. We have the probability that there exists some hypothesis whose training error is epsilon away from the true error. Is that event is bounded on top by the size of h times e power minus 2m epsilon square. Let's consider that thing there. What is that saying? It's essentially saying there is some hypothesis that we are entertaining in our hypothesis space that has a much worse generalization error than the training error. This is an event that is a highly undesirable thing, because it's entirely possible that your learning algorithm will end up choosing that and your learning will fail. Right? So what can we do here? Oh, there's a question on Zoom. If epsilon approaches 0, what does this mean? If epsilon approaches 0, that means that we are demanding that your training error your generalization error must be very, very close to your training error. That means you're placing a very high demand on your a very strong requirement on your generalization error. Again, it's very instructive for me to think of it from the coin toss example. So if you toss your coin 100 times and you ask what's the probability, let's say that there's a coin that I have whose true probability of producing heads is, say, 1/3. 1/3 of the time it produces heads, and 2/3 of the time it produces tails. By the way, I've never seen a coin that does anything but 50-50, but we like using these examples. But anyway, so let's say there's a coin that produces probability of heads is 1/3. And suppose I toss the coin, say, 4 times, and maybe 3 out of those 4 times I get heads. Can happen, right? Just by chance. Then it seems like I have 3/4 probability of heads. So the question is, okay, that's not particularly, let's say 1 out of those 4 times it's heads. So then we are asking, what's the probability that the true error is more than epsilon away from this quantity here? And it says that this expression here, well, not this expression, just this is less than e power minus 2m epsilon square. So if epsilon goes to 0, then you are really demanding that this gap between the true probability and the empirical probability should be very, very close to each other. But you can only get there if you have a massive number of trials. Otherwise, how could you possibly get to an epsilon that's nearly 0? That's really what it means. If you demand that epsilon approaches 0, then you're implicitly committing to conducting a very large number of trials. If epsilon hits 0, then you're implicitly committing to conducting an infinite number of trials. So any small number of trials are not going to be sufficient here. Going back to agnostic learning, we have this expression here. You're asking, we have this bound. What's the probability that some hypothesis that we are considering is really, really bad at generalization time, despite maybe having low training error, despite having whatever training error it has, its generalization error is much worse. And we were able to show that this probability is less than the size of h times e power minus 2m epsilon square. Any ideas on what we can do now? We have done this before. Yes.
Back to Occam's razor.
We are back to an Occam's razor-like procedure. What is that?
Having a smaller hypothesis space is better.
Well, we haven't gotten there yet. We will get there. But how do we get there? What do we do? What's the next step? I do not like this event to happen. This is a situation. This is a really undesirable situation. In a perfect world, I would like that to have 0 probability. We don't live in a perfect world. I would at least like it to have a very low probability. I would like it to have a low probability. How do I guarantee that it has a low probability? Yes.
Do we want to have it as some threshold of like 1 minus delta or something like that?
Well, let's say delta is a small number. I want it to be smaller than delta rather than 1 minus delta. If delta is a small number, 1 minus delta becomes closer to 1. So maybe I would like this quantity to be less than delta. But I really don't have a handle on this expression. I don't know what it is equal to. All I know it's less than that other thing there. So let's draw a plot. So let's say this is 0 and this is 1. let's say this quantity is sitting somewhere here, and this quantity sits somewhere here. I would somehow like for this thing to get all the way down to 0. But I don't know what it is. But I know something else. I know that these two are always, that's, my pencil is not really responding too well today. So let's call this the left and this is the right. The right is always higher than left. The right hand side is always higher than the left hand side. So I would like the left hand side to approach 0, but I can't really control it. So maybe I will try to ask, what does it take to make the right hand side 0? Because if that happens, left hand side automatically becomes 0. But I can't really set anything to exactly 0. The best I can hope for is to make it less than something. So maybe I will put a delta here and ask, what does it take for the right hand side to be less than delta? Because if the right hand side is less than delta, then left hand side is obviously going to be less than delta. That's what we're going to do. So it's an undesirable situation because our learner might end up picking that bad hypothesis, and we would like to make it improbable. And to do that, we will make its upper bound improbable. So we can make this probability less than delta. At this point, the only thing we are left with is algebra. So let's work this out. So we would like to make size of h times minus 2m epsilon square less than delta. If size of h times, so what can we do now? And what do I do? Any thoughts? Take the log. That's a good suggestion because we have this e power and stuff. It looks just ugly. Let's get rid of that. So log size of h, and because of historical reasons in my education, I end up writing log when I mean natural log. It should be ln. But yeah. Okay, let's move things around. This can go here. I've done nothing extraordinary here. I've just moved a few terms around. But I can do a little bit more. I can put parenthesis here and maybe take this thing here. Right? Okay. Well, let me also, while I'm at it, let me also take the 2 here. Okay. But is this starting to look familiar? It's starting to look familiar, but remember in PAC, we cared about 1 over epsilon, 1 over delta. Here we have a delta. Let's get rid of let's change the delta to 1 over delta because we know that log x is nothing but negative log 1 over x. So I like doing math like this, just moving things around. Okay, yes?
Yeah, I was just gonna ask about.
Yes. And we're done. We have an expression that looks very much like what we had before. If you don't really care for my handwriting, I have it written up more nicely here. We have m greater than 1 over 2 epsilon square log size of h plus log 1 over delta. Let's pause here and look at this expression. But first of all, this must look familiar. This is like that Occam's razor expression that we saw before. It's polynomial in 1 over epsilon. It's quadratic in 1 over epsilon. So it's a polynomial. It's polynomial in 1 over delta. In fact, it's even better than polynomial. It's logarithmic in 1 over delta. It's polynomial in the size of the hypothesis space. It's logarithmic in the size of the hypothesis space. The only thing we need is it needs to be polynomial in the dimensionality. but we don't have access to the dimensionality here. But depending on the hypothesis space that you have, you can count the number of functions, and you can take the log of that, plug it in here, and if the log of the size of the hypothesis space is polynomial in the dimensionality, then we are done. There's a catch. What's this epsilon here? Is the epsilon here the same as the other epsilon? The epsilon that we saw before. One person says no. Oh, yeah. Why?
Razor, it's the idea that this error is like the training error is less than epsilon.
Generalization error.
Yeah, generalization error is less than epsilon, whereas here we're seeing if the generalization error is greater than epsilon.
No, it's actually generalization error minus training error.
Yeah, generalization minus training.
It seems like it's different, right? In the first case, it was generalized. It was asked, epsilon was really the bound on the generalization error, whereas here, it's not the bound on the generalization error, it's bound on generalization error minus the gap. The gap, how much worse is it at generalization time than training time? But what did we assume at training time in the first case? Yes. We assumed that. But what did we assume about the training error specifically in the first case? It was the consistent model.
We always thought it was zero.
It was zero. So it's generalization error
Minus training error.
minus zero. So it's kind of the same thing. It's essentially a similar sort of object because the generalization error was, the training error was assumed to be zero there. Let's interpret this expression a bit. So an agnostic learner, let's give it this sort of a learning algorithm a name. An agnostic learner does not care about whether your hypothesis contains the true function or not. It just takes a data set of m examples and produces a hypothesis that has the lowest training error. And then this theorem that we just saw, I mean, I basically proved a theorem. I didn't state it, but I just proved a theorem. What it says is, with probability 1 minus delta, the generalization error is not more than epsilon away from the training error, provided the number of training examples you have is more than this quantity here. If you have a training set that is large enough, and your hypothesis space, your learning algorithm makes a small error on that large number of training examples, there's a good chance that your generalization error will be somewhat similar. Your training error will be representative of your generalization error. That's what this theorem says. There's another way to interpret this theorem. Oh, yeah, but the terms in this expression, there is the gap. Epsilon is how much worse will the classifier be in the future on unseen examples than it was during training, which, by the way, is such a cool thing. I mean, this is a statement about future examples that have not even been seen. We are able to make a statement about data points that are not yet seen using only data points that have been seen. And we are able to make these kinds of bounds, which is a very strong sort of a result. Once again, we have an Occam's razor. This is, by the way, this is also called an Occam's razor. Why? Because there's a dependence on the size of H. This is the Occam's razor for a finite hypothesis space in the agnostic setting. What we saw before was Occam's razor for a finite hypothesis space in the consistent setting. Once again, we have this preference for smaller hypothesis space. If you have a learning algorithm that searches a small hypothesis space and it finds a classifier that has a low error, then it's going to generalize better because it only needs a smaller number of examples to generalize better. There's another way to interpret this expression. It's also a generalization bound. I don't want to get into too much details here. You can get this by rearranging this expression essentially. It says that the gap between the training error and the generalization error is going to be less than some expression that is bounded by the log of the size of the hypothesis space, the log of 1 over delta, and it's proportional to the square root of the inversely proportional to the square root of the number of examples. I don't want to get into too much details about this, but essentially, I just want you to know that you can reinterpret this expression as how much worse will you can actually ask how much worse will the classifier be on future examples. And it's not, it says it's going to be error, the training error, sorry, if I move that error S to the other side, it's the generalization error is going to be less than training error plus this ugly thing here. And if that thing is small, then life is good. To make that thing small, we don't get to control the delta because it's really a confidence term. But the one thing we can control is the size of the hypothesis space. So it is in our best interest to make that thing small. So the best way to make it small is to choose a smaller hypothesis space. Okay, any questions? How would you apply this expression? Or the one on top? Let's work out an example here. This is an example that we have seen before, but suppose you have a concept class. Oh, suppose you have a concept class C. And we do not know what it is. So I don't need to say anything more about it. And now your let's say you have a hypothesis space H, which is all monotone conjunctions. What am I writing here? You know what? Let's make it monotone disjunctions. A monotone disjunction is a function that's like something or something or something, and so on. Importantly, you're not allowed to have any negations whatsoever. Okay? So your hypothesis space is that. What is the number of monotone disjunctions? So if you have n variables, how many monotone disjunctions do you have? There's one suggestion that says 2 power n. Do you want to say why, or does someone else want to counter that?
Be 3 power n because you've got like actually no, it might not be 3n because we can't have negations, right?
Do you want to take it back?
Yeah.
Okay. It's not 3 power n. It is 2 power n. It is 2 power n because every variable can show up or not. That's pretty much it. And there are n of them. So you can have an x1, or maybe you don't have an x1. You can have an x2, or you don't have an x2. And so on till xn. And each of these choices is independent. So the number of ways in which you can construct this expression is 2 power n. Okay, so now I can ask, I have some concept class, and I'm training, I have a learning algorithm that explores all monotone disjunctions, and it tries to find one that has the lowest training error. Now, maybe the concept class, maybe my low training error is not particularly satisfying for me, but this is the set of functions I'm going to explore. Then the question becomes, if you have that, what's the is this going to help you generalize well? Equivalently, I could apply the agnostic learning theorem that we just derived. So if the number of examples m is greater than 1 over 2 epsilon square log size of h plus log 1 over delta, let me plug in the size of h is 2 power n. So this is equal to 1 over 2 epsilon square. What is log size of h? It's, there are constants involved, but basically it is order of n plus log 1 over delta. If you have those many examples, which is just linear in the dimensionality, then life is good. This is a pack bound. We have a pack bound, which means in the agnostic setting, this concept class is pack learnable. Or in the agnostic, we don't say that this concept class is pack learnable. We just say that this is because we do not know what the concept class is. In the agnostic setting, the sample complexity is polynomial in the dimensionality. Notice something else that's interesting here. Imagine that the true concept class was not unknown, but equal to h. Suppose the true concept class was all monotone disjunctions. But let's say you did not know that. Does that make sense? You have a set of functions. Sorry, you have a data set that has been annotated with some concept. I'm the one doing the annotation. I have a hidden set of functions, which is the set of all monotone disjunctions. But at the time that you were running this learning algorithm, you did not know that. And you are applying this agnostic bound. Because you did not know that you were the true set of functions was monotone disjunctions, you had to use this expression. It just so happens that because the true data set, the true function is a monotone disjunction, your function will find something that has zero error. You will get zero training error, but notice that remember, okay, I don't expect you to remember this because it's not something that's necessarily easy to remember, but for the case where you had a consistent learner, the bound was 1 over epsilon It was 1 over epsilon log times log size of x plus log 1 over delta. Importantly, the expression here is 1 over 2 epsilon square. Here it's just 1 over epsilon. So just by virtue of the fact that you did not know that the true function set was monotone conjunction, as a result, you did not know you were operating in the consistent setting, you are forced to pay more examples because epsilon is a number between 0 and 1. As epsilon increases, 1 over epsilon and 1 over epsilon square, as epsilon gets smaller, 1 over epsilon and 1 over epsilon square gets bigger. So just because you did not know that you were operating in the consistent setting, you had to pay more in terms of the training data, which is strange, right? It changed nothing about the learning situation. It just changes something about the guarantee. Basically, having an extra piece of information that you were operating in the consistent setting allowed you to make a tighter statement about the guarantee that you have. With only a smaller number of examples, you can actually state, you can get a better, tighter guarantee. This is an interesting sort of an anecdotal point. Just the value of knowing this extra information makes your bound tighter. Questions? Questions about this example? Or notice one other thing here, which is that the only thing that really matters is what? If I change the hypothesis space, what's the only thing you'll change in your computation? Well, in this computation, what would you change? If I change capital H, the only thing that changes is the size of capital H. So how you compute size of capital H? The rest of the expression is frozen, right? Everything here is frozen. The only thing that changed is the size of H. So if you have a new hypothesis space to see whether it's pack learnable or not, you don't really need to do too many things. You just need to say, compute the log of the size of the hypothesis space. If that is polynomial, life is good. So the same results from before still carry over. Conjunctions are learnable in the agnostic setting. conjunctions have a polynomial sample complexity. Disjunctions have some polynomial sample complexity, KCNFs and all that stuff. But on the other hand, general Boolean functions do not have a polynomial sample complexity. Decision trees of arbitrary depths do not have a polynomial sample complexity. Yes.
So are we saying if given a problem, if we were to have the same hypothesis space, just the knowledge of whether we are working with a consistent hypothesis, a consistent concept versus not knowing it's consistent, i.e. being in the agnostic space, that's going to determine how many examples we need to.
I wouldn't put
Train
it that way. The way you started it was right. I would change the ending of your sentence slightly. Just that knowledge changes how many examples we need to make a guarantee that your generalization error will be less than epsilon.
So we need more examples to make a guarantee if we don't know that we're dealing with
Exactly.
this.
The price you pay for not knowing that you're in the consistent setting is more data.
Okay.
That's what it is. Okay. So let's see what we've seen so far. We've seen an Occam's razor in the consistent setting when the hypothesis space contains the true concept. If you have more than 1 over epsilon times size of h, log size of h plus log 1 over delta examples, then life is good. Occam's razor also shows up in the agnostic case where the hypothesis space may not contain the true concept. In that case, you have to pay more examples because you do not have that extra piece of information. So according to this, learnability depends on the log of the size of the hypothesis space. Have we solved everything? Have we characterized everything we want to know about learnability? We have two cases. Either the true function is in the hypothesis space or the true function is not in the hypothesis space. Are these the only two cases that might exist? Imagine that you have to apply one of these two things to the set of all possible linear classifiers. What's going to break? Infinity. Where? So the size of h is infinite. How many linear classifiers are there? It's infinite. Log of infinite is still infinite. Basically, this bound says if you have m greater than an infinite number of examples, then your generalization error will be low. If I have an infinite number of examples, I better hope that my generalization error is low. It does not tell me anything useful, right? So that's the next thing we're going to encounter. Next. Oh, wow. Okay, we're not going to start that today. I'll give you 5 minutes of your life back. In the next lecture, on Thursday, we will look at how to address the situation where your hypothesis space might be infinitely large. It turns out that we can't address that by just computing the log of the size of the hypothesis space, but we will end up using another technical tool that was invented, I think, in the 60s or the 70s, which behaves like the log of the size of the hypothesis space, called the VC dimension. Okay, we'll see that on Thursday. I'll give you back 4 minutes now. And don't forget to wrap up the project thing and watch out for homework 3. Most likely it won't show up today, so maybe it'll show up on Thursday.